Good afternoon. My name is Miroslav Stampar. I'm working for the Croatian government's CERT, part of the Information System Security Bureau in Croatia. And today I would like to talk about the buffer overflows, the attacks and defenses, what was then and what is now. So this presentation should have lots of technical details in it, and also I'm time constrained to be 50 minutes, so I will try to haste it up so I could present you some of attacks from the most simple to the difficult one that are used in common buffer overflow exploitations. So this is the summary of the presentation. So basically the rules of the game has changed in last decade. So you'll see in the history part from the 2006-2007 defensive mechanisms such as DEP and ISLR came in, and once those defensive mechanisms are used properly, buffer overflows or the attackers using the buffer overflows don't stand a chance. So I'll try to present the both defensive mechanisms and attacking mechanisms, so you could get a grip what was used before, what is used now. So this is the definition copied from the Wikipedia. So buffer overflow is basically any kind of anomaly where the data is written to the buffer, and if it's written in unchecking way, there is a possibility that the boundaries will be overwritten and the adjacent memory will be overwritten. So basically, problem here is that the adjacent memory is in most cases the stack, or in case of the heap-based buffer overflow, the next heap. So in most common situation, either C or C++ will be involved. So buffer overflows are usually going on in the compiled code. In all those interpreted languages, they all have the automatic boundary checking, so this is a kind of legacy from the makers of the C and C++. So that's the way it is now. Hence, lots of defensive mechanisms have evolved, which are protecting the already vulnerable programs you will see later on. Basically, there are two types of buffer overflows. Most common one is the stack-based, and the other one is the heap-based. In stack-based buffer overflow, there is a statically allocated built-in array used. So in C++, that's something like this. So you have the array which is described by these parentheses, and in the heap-based case you will have something like this. So you will have the malloc. So in most cases it's the stack-based buffer overflow. It looks simplified like this. So you as an attacker have the mean to write to the buffer. So it can be any kind of the user input involved, coming from the console or file input or the traffic going on. So if there is no checking of the boundary conditions here, you can easily overwrite these parts here, which are adjacent. Most usually we are targeting this part, the return address of the current function. So this most commonly described as the EAP. So you are taking control of the EAP. If you are able to write here, we will be able to jump to the arbitrary address of our interest in further attack. In heap-based overflow, you are basically overwriting the adjacent chunk here, or chunks, and this is the more trickier way to. This is more trickier to exploit than the stack-based. Thing is that you are targeting this metadata part. In most cases, or the old attack, there is a newer one, but in the practical mean, you are targeting those pointers that are part of the metadata of the adjacent chunk. So there is an attack where you are writing the chunk and its metadata, and if you are able to write the arbitrary addresses into those pointers, there is a way to write also the data to addresses of your choice and to take over the control of the program. Vulnerable code in the stack-based case looks like this. So basically you have the statically allocated buffer here, and you are using some kind of the unsafe C++ function. In this case, there is a string copy. So if the input data here is bigger than 100 characters, this buffer will be overwritten. In the heap-based case, you have the two heaps allocated, one near the another, and if the attacker is, or the user is writing to the first heap, if the user is writing a large piece of data, it will be also able to override the content of the heap and the metadata of the heap. History goes like this. So in 1961 there was an excellent protection in those old 2-3 bedroom machines that was called the executable space protection, which is now commonly named as the data execution prevention and the no execute you will see in following slides. So basically we had the means of protection in 1961, or at least the part for defensive, but later on it was not used in later years. Also, out of more interesting things going on, there was the case with the smashing the stack for fun and profit. This is the article written by the Aleph Fund. You most probably heard about this title. Also, there were two popular worms going on, Morris worm and the Code Red, which exploited common exploits in those days, which were also the buffer overflows. Also in 2004, you can see that this protection NX and DEP were introduced to the Windows and Linux. After that, the attacking difficulty became harder and harder. We'll see later on. Also, you can see here there are a mix of Visual Studio Flag GS and the GC Flag F-Stack Protector that are today used in the compiling of the system libraries. Also, they are recommended to use in other cases. So basically, what those flags do, so you're programming your code, and if you use those flags, it will just warn you or prevent you from compiling any further if the buffer overflow is found in the code. So basically you have those strong protections implemented in 2004 and 2005, so NX, DEP and ISLR. Also there are those flags used in the case of the Visual Studio here, and the case of GCC. So basically after the 2005, the exploitation, at least in the system part, came extremely hard. So if you are reading the exploits that are coming lately, you will see, at least in the case of the Linux system exploits, so particularly in the part of the privilege escalation, you will see that all those exploits are not buffer overflows, but the common logic bugs. So in lots of cases there is some kind of race condition going on where the attacker is using the privileged mechanism to introduce its code into it. So basically it doesn't have anything to do with the buffer overflows. So this is the first defensive mechanism I would like to introduce. So basically what it does, this data execution prevention of or no executes. This is the data used in the Linux part, this is used in Windows world. So basically what it does, in most common words, it prevents you to put the programming code into the stack and to later on to execute it. So any kind of buffer overflows doesn't, if you are able to exploit the buffer overflow, you won't be able to introduce the programming code to the stack. So you won't be able to exploit it, at least in this most simple way. Later, there came the ISLR. So this is the other space layout randomization. This is the other piece of the puzzle which bothered people that want to defend the systems. So basically there is another way how to exploit the buffer overflows if you are not able to introduce the executable part into the stack. Later on you will see that it's called return-oriented programming. Thing is that in lots and lots of attacking scenarios, attacker needs something to jump or needs some solid address to call, so he could be able to introduce some functionality into his payload or shellcode. So basically, if you want to call the system address or system function, you need to know the exact location of that system function in the current programming's address space. And if you are able to, or you use this defensive mechanism, those system function addresses will change each time you execute the executable. At least in the Linux world, those addresses are changing each time the program is run. In the Windows world, those addresses are changed when you reboot the machine. All the system functions will just change the address where they are located. So basically, for example, if you want to run some Windows function like winexec, you will see later on in one example. If you want to run the winexec, which will call the cmd.exe in the Windows world, you won't be able to run it because you won't know what's the address of that winexec function in the programming in the program's virtual space. Stack canaries. This is the one simple defensive mechanism that was introduced with the compilers. So basically, writers of the compilers introduced one random value. Most commonly, it's random. It's being put just before the program parameters and the return address, and if this same value is overwritten by the buffer overflow, then after the part of the function where we could be able to take over the execution control, there is one mechanism implemented by the compiler which checks the stack canary. If it's missing or it has the invalid value, it will just discard the further run. So basically, stack canary is nothing more than the value that is written just before the end of the buffer, and if it's being overwritten, it will prevent you from further exploiting the buffer overflow. ASCII armor is the fancy mechanism where the system functions are enforced to use the 00 character in its address. So if you know basics of the buffer overflow, you'll know that the 00 is a big nemesis of the buffer overflow. So basically, in 99% of those vulnerable functions like string copy, if there is a shellcode using this address, so shellcode wants to use the function like system on the Linux world, and it has this 00 in its address, it will just, string copy will just stop the copying of the buffer, so it will just skip the later part of your usable or malicious payload. So this is basically a simple way how to prevent the usage of system addresses. A structured exception handler. This is something that is being described in the tutorials for the buffer overflow exploitation as the system to prevent buffer overflows, but the system wasn't primarily introduced for the protection of the buffer overflows, but just for the sake of properly doing the exception handling. So if you know the basics of the object programming, you know that if you have the couple of exception handlers that are involved in the programming logic, you know that there is certain priority of those that needs to be run if there is an exception going on in the program. So basically, what is being done? This is the simplified version of the structured exception handler chain. Basically, if there is an exception going on in the program, first the program is handling the handling to the first exception handler. If that exception handler is not able to process the exception, it just goes to the next exception handler. It just bypasses the control to the next exception handler. If this doesn't, if this one is not able to process the exception, it goes to the final one. And if this final one is not able to process the exception handler, you will see that nice blue window, or not blue window, but the dialog that says something like access status valid, invalid, so on. So I'll show you the mean how to exploit this chain here later on. Basically, this structured exception handler is something that is used a lot by attackers. C-hop, that's the protection mechanism introduced to protect the SEC. So guys from the Microsoft, they saw that lots of new exploits use the bypass of this, or use the mechanism used in the structured exception handler. So they introduced the protection of that same mechanism. So one is C-hop. Basically, what C-hop does, it links the one symbolic exception handler here to the end. So each time the exception is being raised, if the chain is not properly being built, or if it's being overwritten by the buffer overflow, the checking mechanism won't be able to go to this last exception handler. SafeSeg is the similar protection mechanism where all the exception handling addresses are collected and entered into one table, separate table, and each time the exception is being raised, all those exception handlers are being checked. So you don't have to memorize all this. I will show you the ways how to exploit SEG, and I hope that you will see what's the problem here. What's the problem introduced with this mechanism. Set functions are also one of best methods how to deal with the buffer overflow protection. So basically, instead of using of all those unsafe functions, the new safe functions were introduced, where the explicit parameter size was introduced along the standard parameters here. So basically, if you use the difference between string copy and string L copy will be the size parameter. So what it does, you give the size of the buffer to this safe function here along with other parameters, and there is no way how you will be able to overflow the buffer, because the function itself won't copy nothing more than the size itself. So now we are going to the attacking part. So now I will show you the attacking methods used from the most simple to those more complex. So knob sliding, knob ramping, knob sliding, something that was used in those older exploits. Also, this is a method used in the heap spraying, if you heard about it. So thing is that instead of using one shellcode that is, for example, 300, 400 bytes long, you extend it with lots of dummy operations called no operation, and you jump to the address that you hope that will be just in that NOP part. So basically imagine that you have a large ramp of no operations which are harmless to jump into it, and at the end of it, it's the usable malicious code. So what's the purpose of this attacking mechanism? Purpose is that in lots of cases, all those older cases, stack is something that was unpredictable, but in those older days, stack was something that you knew that it will be along this other space, but you weren't sure that it will be the exact address. So you just use the knob sliding, so you introduce the large, for example, several megabytes of those knob operation instructions, and at the end you introduce the shellcode, and you just use the address in between of the knob slide to jump into it. Return to libc, also known as the returns to system or ARC injection. This is the attacking mechanism used to most commonly to exploit some kind of suite. You know what's this suite application? So this is the application that in one part has the highest privileges, and if you are able to introduce your code at the time of running of that same program, you will be able to become the root or administrator. So in a return to libc, in most cases, you want to introduce or you want to run the shell. So you're introducing into the buffer overflow the mechanism to call in this case, the function system, which will just use these parameters from that are passed here. So as this is the linear scale, so this the way how the buffer is being written, or this the malicious buffer. So basically you are using lots of junk here, so those characters are just used to come to this feed part. Feed part is the address itself, where you want to introduce, or where you want to take control of the execution mechanism. So basically it's called ELP, so it's the instruction pointer which you want to overtake. And if you, in this case, if you overwrite it with the address of function system, in case of Linux, and if you introduce to the stack the address of string bin sh and the address of function exit, you will be able to raise the shell out of the vulnerable application. You will see at one example I show you later on how it's being done. Return to register. This is one of the 101 exploitation methods, also known as the trampolining. Thing is that in lots of cases when you are able to do the buffer overflow, you will see that the one of register will contain just the appropriate address for you to use for the proper jump. So in case of the NOPS threading, you needed to introduce the static address. It was problematic because stack can be viewed as the deterministic mechanism. In case of return to register, you're all passing that problem, because in most cases ESP, or the stack pointer register, will just point you to the address just after that sweet spot where you have overtaken the instruction pointer. So basically how the malicious buffer looks like. So basically you are trying to buffer overflow, using lots of junk characters here. After it, you use one address you have found previously to the jump ASP or call ASP instruction. So basically, if there is no ASLR defensive mechanism used, you can use one static address which has the jump ASP or call ASP instruction, and when the buffer overflow kings, or when it's being taken, when it's being processed, this address will be used to be returned to it, and it will just be used to jump to the ESP or the call ESP. So you will be able to jump to the location which the ASP is pointing. And in most cases, ESP just pointed to the afterwards, after this address itself. So this is a great way how to bypass that constant address problem. So you're just jumping here, and afterwards you use this payload here for the malicious purposes. So either reverse shell or something like that. You will see these compensating knobs in lots of these examples. Thing is that you always need to expect the payload to use the stack itself. So you don't want the payloads to push something or pop something from the stack. If the stack pointer is pointing to the payload itself, it will just overwrite itself. So you're always trying to use some, in most cases, 8, 10, 16 knobs are used just to compensate that space that could be used by the stack push or pop in the payload part. Egg hunting, this is something quite interesting to be used. So if you will have the wish to further play with those attacking mechanisms, you will see that the egg hunting is something really fun. Thing is that there are cases when you know that you can see that you can do the buffer overflow, you can take over the execution, but afterwards you have something like 50 to 100 bytes that are usable for your execution part. In most cases, payloads, those useful mechanisms like payloads for reverse shell, they are large in size, like 350 to 500 bytes. So you have 50 bytes which you can use for the execution, but you need to squeeze somehow the 350 bytes. So here comes the egg hunting. You use the small execution mechanism which will search the further in memory if there is any kind of if there is an occurrence of this same buffer which is not trimmed in any way. So you could just jump to that uncropped buffer. So, for example, using one practical example, you will see that the useful part will be 50 bytes. You can put anything useful into 50 bytes except the egg hunter. And you'll see that the egg hunter will be able to find the whole, in this case was the HTTP request. So one header was prone to the buffer overflow, and the egg hunter that was introduced by this same header value was being able to find the whole HTTP request inside the memory. And once it finds the whole HTTP request inside the memory, it jumps to the payload inside this larger uncropped buffer. So how it looks from this malicious buffer perspective. So basically, you want to come to the buffer overflow parts. You introduce the egg hunter here. You use the address of jump PSP. So this is the more complicated way. I could also use the simple way, but stick to me. It's like this part is used for the execution, to take over the execution part. It jumps here, this part jumps here. Egg hunter is trying to find the egg itself inside the memory. When it finds itself, the egg inside the memory, it just jumps to this larger part. You will see it's better in the practical part. So basically, you have one execution mechanism which searches for the bigger one. Basically, there are currently 4 or 5 different egg hunter types. It looks something like this. See, it's not clearly readable. It's lots of assembler going on. But in that small space, the whole other space is searched for this particular payload. So you have the payload which has the mark you were put there, and the egg hunter is searching for that exact mark, and it jumps to the payload afterwards. The things with the egg hunter types is what's also cool about them. Things that they are going through all memory pages without triggering any exceptions. How is it being done? Things that there are low Windows functions which can be called that won't raise you an exception, but it will just say you, it will just return you a value which will say to you, okay, you don't have the read permissions here, please move along. And this egg hunter will just go each page. It will just read all the memory content and search for the egg or the payload itself. Afterwards, if it finds it, it will just jump to it. Safe bypass, as said, this the attacking mechanism. It's popular, or it was popular. Thing is that problem with the safe bypass, or problem with the structure exception handling, is that all those pointers that I drawn here, those pointers to the handler and the next exception handler in the chain are put onto the stack. So now imagine that you are able to overwrite those pointers, and once you do the buffer overflow part, in lots of cases exception will be raised, and if you are able to override those pointers to the piece of code that you control, you can just execute the shell code afterwards. So what's the useful part here? Thing is that this pointer to the next stacked exception handler is all written by the jump to payload instruction. This the instruction which is being called by the structure exception handler from here. So once the buffer overflow raises the exception, if you control this pointer, which is here, you will be able to execute those three instructions, which will pass the control to here, and this part will just jump to your payload here. So it looks like it's complicated, but once you do a couple of those, you will see it's really something that it's repeatable, something that can be easily be used in further exploits. Like this part is just all written with the exact 4 bytes in all cases. So it's EB06, which will just jump here, and in this part, this address, the sequence of commands needs to be found previously in the programming space. You will see later on how can it be done. Afterwards, the payload is just concatenated here. Roping, or the return-oriented programming. Now imagine that the DEP or NX mechanisms are enabled, or data execution protection. So you as an attacker, you are able to do the buffer overflow, you are able to override those weak parts, but you are not able to execute anything from the buffer itself, because all the buffer is marked as non-executable. So some clever guys thought about how to overcome that obstacle, and they invented the return-oriented programming. What is it all about? Thing is that you don't need the instructions. You don't need the binary of instructions to be able to execute anything. You can just use addresses of instructions in sequence, which can be used by the stack or by the read mechanism. Things that you push the return addresses of sequences of commands, which will end with the red command. Thing is that imagine that you put the address of the increment AX red command sequence. Afterwards, you put the address of the sequence which calls some system function. Afterwards, it has the red. So once the buffer overflow tries to execute or tries to return the execution to this part in your buffer, it will just return to each of those addresses execute those those instructions. It will do the return, but the return itself will just jump to the next. It's called the ROP. It will just jump to the next address. It will call this next address. That sequence will end with the red. So you are able to just jump from here to here by just using those addresses. So it's a popular mean or popular way how to use or how to exploit buffer overflow, particularly in those newer versions of Windows. What's the purpose of return-oriented programming? Things that it's kind of complicated, but there are means how to call the system functions which can just disable the data execution protection. And if you are able to do that with the ROP chain, or you are able to call one of those functions, you will be able to disable or you will be able to mark this part as from non-executable to the executable of that same buffer. You were able to overwrite, and afterwards the execution will just continue with your binary payload. So you are just using the return-oriented programming to disable the protection mechanism here. Afterwards, the execution just follows on here. Heap spraying. This is a buzzword that can be read in lots of newer exploits. Things that lots of browsers are attacked with this. As I have I'm time constrained, I'll just say a couple of words here. Things that in heap spraying, you are able to overtake to do the buffer overflow, to overtake the EAP or the address where the execution should continue. But instead of using the return-oriented programming, you can use the heap spraying. Heap spraying goes like this from the visual perspective. You're trying to introduce the large blocks of the knob slides and your useful payload. So things that you are just copying payloads together with the knob slides in large quantities inside the memory. Things that heap is something that is becoming deterministic after a couple of calls. So if you are able to introduce lots of those large chunks with the payload and knobs, after a while you will see that the chunks like this will be introduced to the memory with the predictable memory addresses. So things that these are lower addressing space. This is the lower addressing space, I know, with some common browser, and things that if you do lots of heap spraying, you introduce one large chunk like here, and you will be able to jump anywhere inside of this part. You will be able to execute the payload itself. Now the demo time, I'll show you. I have 10 minutes, 15 minutes. Try to. How much time do I have? Doesn't anybody know? No.
Just keep going.
Okay. I'll need to sit down. So this is a large area to fill in 15 minutes, but I'll try to just show you glimpses of the exploitation. I prepare 5 examples. I will try to keep up the pace. So return to libc. This is the proof of concept. So basically how all the exploitations begin. Somebody somewhere finds a way how to buffer overflow something, and he writes the proof of concept to the exploit DB. You find the proof of concept like this, and you try to exploit it. So basically, this BOFE is a simple buffer overflow application that I made, just to show you how the return to libc works. It looks like this. So it's a pretty basic buffer overflow. So if the data of more than 100 bytes is introduced, buffer overflow takes over. So how it looks like here, I'll show you. This is the platform I will use to perform the exploitation. So this is the buffer overflow path. So it just has run the application, the 200 A's here. So return to libc goes like this. So you were able to overwrite the EAP. The first thing you do, this is the 101 of the buffer overflow. You use the pattern create from the Metasploit. You say what's the size of the buffer. You see the size of the buffer is 200 characters. So 200 characters you've seen here from the proof of concept. You fill this with this special 200 character string. Afterwards, you run it inside the debugger. So you run the BOF. You say arguments here are this same string. You set this. It next you need to restart. You restart. You run it. The exception or not the exception evaluation is raised here. You see this character or this value here. This is the special value. This is one of those values coming from that same special string. There is a nice or this is a plugin for the immunity debugger, which is commonly used by the exploit developers. It is now used also in the Win debugger. I'll show you here how what is it used for. This is the Swiss Army tool for the exploitation. So now I will ask the monad to find all the. It will just go to the process address space and to try to find these special characters from here. You can see here that the AP was all written by the same value, and the offset of this same special value was the 112. So basically what it says, this monad is expecting this same special a string coming from Metasploit's pattern create, and it says to you that the buffer overflow is taking over the AAP register after 112 characters. So basically what it says to you, that if you do this, afterwards you are taking over the EAP. So I'll show you. You always need to also, this is the 101 of exploitation, you also always need to take care of the final buffer size. So if we started with the 200 characters, you need to end with the 200 characters, because in most cases it will just something will go out of boundaries and you won't be able to exploit it. So we'll try to restrain the buffer size to the original size. It was 200 characters. to just fill the buffer. Here comes the sweet part. In case of the return to libc in Windows, you want to call the winexec. Afterwards, you want this to be the return address after the winexec is being called. Here you need to put the address of the cmd.exe, and here you can put 4 bytes of junk. Because this is the something I'll show you. I'm not improvising here, because this is the exact commands or exact parameters that need to be passed to the winexec. Those two. This one is dummy. You can put here anything. Here you need to put the address of the cmd line or cmd.exe. Here this is the return address after the winexec is being called. Now, how to find the winexec address? You can find it like putting the breakpoint to it. You'll see that the address is this. This is constant, at least in the case of the Windows XP SP3. So basically, you are putting this value in low Indian order here. This is just the function called to extract pack to unpack this, or to pack this value to the 4 bytes in low Indian order. Exit process. So you put the breakpoint to the exit process. You copy the address. You copy the address here. Address of cmd.exe. Cool thing about Mona is that it provides you a way how to do this. So you can search the whole address space for the cmd.exe. You try to find it. Here you can see one address which has the 00 inside of it. You don't want to use it. As you recall, 00 is the enemy of buffer overflows. But you found this address here. So it's coming from this library. You just copy it here, and 4 bytes of junk. So basically you can put here. Common string for junking is, show you, for junking is that big. But you can use whatever you want. So basically, if you run this now imagine that this BOF, imagine that the BOF is privileged program, and if you run it like this, so it would just call the BOF with this special buffer. You can see this. So basically, you have taken all you have called the winexec with the shell part. So this is the shell coming out of the program itself. If you run the program itself, you won't get the shell. So get the point. So this is the first example. So this is dangerous for the privileged applications. So if you are able to overtake the privileged application like this, so win. Afterwards, the second PSC that I want to show you. So it goes like this. Somebody, so this is an imaginary situation, a scenario. Somebody has posted the POC for the free float FTP program. It's a free program like this. So somebody has posted it here and you want to exploit it. You will see in lots of those POCs bad characters. Bad characters as something that the original creator of the POC has recognized that those characters are bad for the further exploitation, and you will need to avoid usage of those characters in your buffer. So here you put the address. That's the address of this FTP server. So let's run the FTP with the debugger. We run it. So let's just skip this part as there is no time. I'll just create that special pattern with the 1000 characters like this. We'll copy it here and we'll just run the POC. Here you can see also one special value coming from the buffer overflows. From the buffer overflow program, we will say to Mona, please find all those occurrences of those special characters. It said to us that the EAP was written one of those special values from the offset 247. You just use that same knowledge, so you just fill the 247 junk characters like this. Afterwards, so this is the padding part. So you want it to stay in the 1000 bytes character range like in the original POC. So it goes like this. So here, this is the example for the return to register. But here you want to say the address of jump ESP or core ESP, which will just give you a control. Here we will see puts a couple of compensating operation instructions like I told you. I use only 16 bytes, and afterwards we'll put here a payload. Payloads I've used in all those examples. Payloads that was created with like this. So reverse TCP toward our address port 444, and you want to, in all those cases, you want to put the bad characters. So MSF and code will just take care that none of these bad characters are coming into our payload. So just to hasten up, I will just copy paste the payload. So basically it should be the same as this. So payload part. So this is the payload for the shell code, reverse shell code. We want to run the netcat listener on port 444, and that's basically it. So you can see we filled everything except the address of jump ASP call ASP. Mona to the rescue. So Mona has a nice command. So it's called jump. So basically you tell Mona to find all addresses which would jump to the ESP register. It goes and goes and goes. It will take 10 seconds. Okay. Afterwards, now you don't need to afterwards, these parts are of interest to us, because these parts are telling you that this instruction is coming from the page which is protected by those flags or those protect mechanisms. In this case, ISLR is okay. I will just cut it. You can just use the first usable address from here, and we will just put it here. So basically this is the jump PSP address. So you have the jump PSP address, compensating knobs, payload, and this padding part. So just to now we will just rerun the vulnerable application, and we have the listening shell here, listening netcat instance, and we'll just run our application. Oh, not here, but the expected. This is the expected final result. So we have the shell toward the attacked machine. So we have taken over the machine or the vulnerable FTP application. So this was the example for the return to register.